Everyone. So I'd like to talk about wallet design, the basis for client-side security and authentication really is wallet design. Everything we're doing, you're doing in this room will rise or fall based on whether we solve this. We present a model for authentication and metrics for evaluating wallets for the first time. And those immediately reveal some surprises, as you'll see. We present novel design and analysis tools, and these are directly applicable to actually working solutions, and we'll see they improve the state of the art. Results here include work with Deepak Maram and Mahimna Kelkar. So what I'm going to discuss here actually touches on all digital assets, from cryptocurrencies through NFTs to what will run on central bank digital currencies one day. They all boil down to keeping your assets safe with a wallet. So this will be relevant for individuals storing their own keys on their phones, to companies storing large amount of money, same concept, different details. For asset management corporations that manage the funds of others, and in fact, even beyond the context of blockchains and cryptocurrency, all authentication. And in a decentralized world, everything is harder when we want to authenticate. And why? Because there is no office you can go to and say, look, I forgot my password. There is no credit card company you can say, my money was stolen, undo the transaction. No one to appeal to if you lose the money or if you are attacked. And additionally, there's too much at stake. Anyone accesses your keys for 1 second and it's gone. Now, there's been a lot of previous work that supplied a plethora of tools, from MPC, tools for securing individual keys, to designing K out of N wallets, etc. A lot of tools going a while back. And the question is, what do we do with all these tools? So we know a little bit, right? We know that we should secure our individual keys well. We know that K out of N is not a bad option, K out of N wallet. But is this enough? No. Just from last year, to huge attacks or loss events lead us to understand that we need better hold of how to address these problems. To do this, we'll try to first understand the problem we're looking at. We have a blockchain, and we have users sending orders and transactions to this blockchain. The contracts are visible to everyone. You can see what the others are using for security. The authentication is typically done with cryptographic keys, not with passwords, though we'll talk about those too. And the users are in charge of maintaining their secret keys, so the attacker doesn't have them and they don't lose them. And the goal of the wallet, the authentication mechanism, is to make sure that you can access the money and the attacker cannot access the money. We all know this. To really think about things deeply, we'll need to understand the model. And here is the model. So we first need to talk about the credentials. This could be a password, a physical device with a PIN code, a safe deposit box somewhere, and physical implementation of a 1 out of 6 threshold signature, as you saw here. Now, individual credentials can be safe, meaning you have them, or they can suffer faults. So if the user has access to the key, but the attacker does not have access to the key, we say the key is safe. That's great. If the user does not have access to the key and the attacker also does not have access, we say that the key is lost. If the user has access and the attacker also has access, the key is leaked. And if the user loses access and the attacker does have access, we say that the key is stolen. What does this translate to? For a password, if you forgot it, that's loss. And a leak is if the attacker guessed your password. For the physical device, if you can't access that safe deposit box, then it is stolen. For that device with a PIN code, it's lost if you either forgot the PIN code or lost the device. That's loss. And for it to be stolen, the attacker needs to get hold of the physical device and guess the PIN, and so on. So we translate the actual credential into just these 4 states. Now, here is the full model of everything. We have a user, we have an attacker, and we have the wallet, the authentication mechanism. I'm saying just one attacker here. Obviously, we have many attackers trying to get our money, but this is like the worst attacker at the worst time that got hold of the most credentials. Now, each of the user and the attacker have some keys. Here, 2 keys are safe, the blue and the green, and the silver key is leaked, so both the user and the attacker have it. Now, both of them are going to try to identify to the authentication mechanism and say, send an order to move money. This could be a transaction, maybe with a transaction ID. If you access an online service, this is a session ID cookie. We want to abstract that as well. So we have an environment that gives each of them an ID. So here the user has ID 1 and the attacker has ID 0. It could be the other way around. Each of them know their ID, but the authentication mechanism does not. The authentication mechanism has to guess or understand which is the actual user. And this is done by communication. The user and the attacker communicate with the authentication mechanism, and then the authentication mechanism decides. And the user will be successful if the authentication mechanism said this is the true user. And now we can talk about scenarios. So we have the, say, n keys. Each of the keys can be in one of the 4 states, safe, loss, leak, or theft. And then the vector of n keys is the scenario. And given a scenario, we can derive the availability vectors of the user, the owner, and the attacker. So if the key is safe, then the user has it and the attacker does not. If it's lost, then both of them do not have it, and so on. Now let's do a probabilistic analysis of how secure we are. So for this analysis, we'll assume that the keys have probabilities of suffering each of the faults. Yeah. So each key has a probability of being safe, lost, leaked, or stolen. And for most of the examples, we're going to assume the probabilities are the same, right? So each key can be in a different state, but the probabilities of all keys to be lost are the same in most examples. So we have 4 to the n possible scenarios because of the 4 states, and for each state, for each scenario, we have a probability and the availability vectors. Now, what's the wallet? Now we can talk about the authentication mechanism. The authentication mechanism is simply a predicate on the availabilities. It receives credentials and it needs to decide user, not user. So in other words, it's a Boolean monotone function. It takes the availabilities, 3 availabilities, and returns yes or no. This example says I accept if I get key 1 and key 2, or alternatively key 2 and key 3. For example, key 1 alone or key 1 and key 3 are not enough. And now, the user can be successful, the attacker can be successful, or neither of them can be successful, or both of them can be successful. We say that the authentication mechanism, the wallet, is successful if the user can take the money and the attacker cannot take the money, cannot satisfy the expression. So we're conservative here. We're saying if the attacker can take the money, it will be quicker than the user, and we're not in a safe situation. And now we can talk about the probability of failure. That's the probability of an unsuccessful scenario. Okay? If you lost me for a bit, you can come back on the wagon now. So here I'm showing you the best wallet for different probabilities. In all cases, we're going to have a theft probability of 1%. And then each point here has a certain probability of leakage and a certain probability of loss. And you see that if leakage is likely and loss isn't, then we're best off with the 2 out of 2, the AND key. We'll require both. It's unlikely that the attacker will get both. If loss is more likely, then we're better off with the OR key, or 1 out of 2. So even if we lose 1, we can still access our funds. But the interesting thing is this sliver in the middle, and it becomes more pronounced with a theft probability of 4%. You see here, and this is actually the region we're interested in, right? Where loss and leak probabilities are small. We're going to choose keys that have small failure probability, fault probability. And you see that in this most interesting area, the best wallet is actually just to use one of them, not use AND or just choose one of the keys and use just one rather than 2. That's an interesting surprise. Now what happens with 3 keys? With 3 keys, the graphs becomes a bit more interesting. This is with loss, and again, the interesting part is over there, and this is good news because a lot of the services you might be using actually use 2 out of 3, and now we can formally argue that this is going to be optimal, at least with these probabilities. Now what happens if we go up to 4? Should we use 2 out of 4, or 3 out of 4, or maybe something else? So again, it depends. If loss is more likely, then we should be more lenient, and we'll take the 2 out of 4. But if leak is more likely, then 3 out of 4 is better. Can you guess what happens if we add theft into the mix? This is without theft at all. It becomes interesting, right? I told you it will be surprising. So I'm not going to go into this at all. Instead, let's move up a level and talk about what happens as we increase the number of keys. And this will also end up with a surprise. So my first question is, can we just scan and check all possible wallets? So wallets, like I said before, are monotone Boolean functions. They take the availability vector, true, false, false, true, and they return true for success or false for failure. Now, if you have an additional key, it's never going to harm you. So it's a monotone function. If you have 3 keys and now you have an additional 4th key, that's only going to be good. So it's a monotone function. So the number of wallets is the number of monotone Boolean functions, actually -2. Because constant false and constant true are also monotone functions, but we don't care. Now, the number of monotone Boolean functions is called the Dedekind number. Dedekind discovered it in the previous century. Here we have, see, with 0 keys, there are no wallets. That's Dedekind -2. With 1 key, we just have the 1 wallet K1. With 2 keys, we can use either of them, the AND wallet and the OR wallet. And with 3, we have more options. Now, can we scan all of them? This is what happens when we go to 5, still manageable. But these are actually all the Dedekind numbers we know. So humanity does not know what's the next number for 9 keys. Certainly, we cannot go over all of them. So beyond a certain number, we're going to have to resort to heuristics. And this is what happens. I'm going to show you a couple of these, so let me just explain. We increase the number of keys here from left to right. 1 key, 2 key, 3 key, and so on. And on the y-axis, we have the failure probability of the wallet. So if you have only leakage, all keys have the same leakage probability, you see that the failure probability drops exponentially. The y-axis is exponential, is logarithmic. So the failure probability drops exponentially with the number of keys. If we only have loss, same story. Now look what happens when we only have theft. The general trend is still exponential down, but there is no benefit in going from 1 key to 2 keys, from 3 keys to 4 keys. This kind of repeats what we saw earlier with just 2 keys. And here's the big message here. I'm showing here plots for the situation where we have loss probability of 1%, 2%, and 3%. So this is 1%, this is 1%, this is 3% loss probability. All keys have 1% theft probabilities. What's the message here? With 6 keys that have 3% loss probability, you have an order of magnitude lower probability of failure than if you used just 3 keys with way better, 3 times smaller loss probability. So quantity over quality. If your answer to security is let me keep a single key in the deepest safe I have access to, this tells you this probably is not the right answer. No, I don't want to expose and ask everyone's personal choice, but you can check whether you're happy with your life choices with this small research prototype we have. So no warranty and anything. This is a research prototype. You give it the probabilities of the faults of your keys, and you can actually design your own wallet or ask it to find the optimum, and it will calculate the failure probability. So this is a research project, but it's a good one. It's got the first prize in the hackathon for the IC3 bootcamp last year. And importantly, everything is computed locally on your browser. So it's all C compiled to WASM. Nothing goes outside your computer. You're not revealing anything when you experiment with this. So all this is nice and well, but we can do better, a lot better, with interactive authentication. Interactive authentication is relevant where when the communication channel between the user, attacker, and the authenticator, the wallet, is synchronous. So you have the authenticator can rely on sending a message to the user and getting it back. This is our reality with blockchains, because once we see an operation on the blockchain, we know that the actual user has seen it within a bounded time, assuming they're connected to the network. And this actually goes back to work with Gun Sear that we did during my postdoc with Multimuser called Bitcoin Vaults, but that was a specific case, and here I'm going to go general. And by general, I mean we're actually going to go even beyond probabilities. We're going to talk about profiles. So profile is the set of scenarios where a wallet succeeds. So for example, this is the 1 out of 2 profile. You get success if one of the keys is safe and the other is either safe or lost. The end, you are successful if one is safe and the other is either safe or leaked. And this is just using just one key. And this definition of a profile allows us to define an order, a partial order on mechanisms. So a mechanism that achieves this profile is better than a mechanism that achieves this profile because its successful scenarios are a superset of this ones. They can also be not comparable, so neither is a superset of the other. We're not counting checks, we're looking at supersets. So can we find maximal mechanisms? What's a maximal mechanism? It's a mechanism where there's no mechanism better. And I'm going to give you a template for designing such mechanism. The template is going to go as follows. Your wallet receives credentials from one party, receives credentials from the other party. It can wait because we're living in a synchronous world. And then it puts both of them into a judging function, will denote J, and the function J will actually define which is the true user, hopefully. So here's a simple one, the priority mechanism. We define a priority over the keys, so purple beats silver beats gold, and we'll choose the winner to be the one with the unique highest priority key. So in this situation, the user has the purple key, so it's the winner. In this situation, both have the silver, so we don't care, but only the attacker has the gold, so the attacker is the winner. And here is the profile for the priority case. So if you remember OR, AND, and one key, so all of them are weaker than the priority mechanism. And I am afraid I'm out of time. I will only tell you that we have a bound so we can prove that this is actually a maximal mechanism. You cannot do better. And one last thing, please. For 2 credentials, these are new mechanisms, so we introduce actually the best mechanism for 2. And beyond that, this is the Argent wallet, solid design, actually the best I know in terms of profiles for cryptocurrency. They have a rich procedure set. And by analyzing this wallet with our tools, we were able to actually improve it because we had the formal methods and techniques. And we showed that the mechanisms we provide are strictly stronger, achieve strictly better security. Thank you very much. I'm out of time.